Okay, next up is Khola Jamshad.
Yeah. Hi, so I'm Khola, and I've been working with Dr. Jackson at the University of Michigan on modeling cancer evolution, which shouldn't be too surprising since we're at a math oncology conference. But in specific, we're using a data-driven agent-based approach to intratumor heterogeneity. So the way that we look at intratumor heterogeneity is by essentially studying the branching evolution process, which describes how genetically distinct subclones arise in a single population. So here's just a branching evolution process kind of diagram. At the initial stages, we have driver gene mutations occurring that confer fitness advantages to certain clones and promote clonal sweeps where that subclone takes over the whole population. What we're really interested in is looking at the progression phase of this, where because of the high genetic instability, you get a lot of random mutations occurring, which are either private to a subclone or a group of subclones, and you want to see how that heterogeneity emerges and then impacts drug resistance and the evolution of the tumor moving forward. And we're looking at melanoma. Was there a? Yeah, so we're looking at melanoma because of its high somatic mutational burden, and also because it has a really high relapse rate when it comes to treatments, which is associated with the existence of certain resistant subclones. In particular, we're looking at the most common type of melanoma, which is a slow-growing, superficially spreading melanoma. To tailor our model for melanoma, we kind of shortlisted 7 different genes, driver genes, that are associated with it based on how commonly they occur and also how much they contribute to the heterogeneity of the tumor. So for superficially spreading melanoma, it's associated with a BRAF mutation, which is the one at the top. And interestingly enough, in literature, it seems that the first 3 driver genes that you see there, BRAF, NRAS, and KIT, are mostly mutually exclusive. So we ended up including that in our model. And we're looking at hallmarks. So for most of the models that we saw, there was either a focus on a single hallmark or at most like 2 hallmarks. And we really wanted to see how multiple hallmarks could be integrated in our model and the effect that their interplay would have on the progression or evolution of the tumor. So we looked at increased proliferation, survival, immune evasion, and then the enabling characteristic of genetic instability, all of which happen to be associated with a BRAF mutation. And then from these 4 hallmarks, we kind of mapped onto the genes, whatever hallmarks they were associated with. And then we built an agent-based model to put them in. So our model has 2 agents, melanocytes, which are just the normal melanocyte cells. They have a genome associated with them with 50 genes, of which D equals 7 are the driver genes that we just mentioned. They also have an antigenicity, and they are stationary when we focus on modeling superficially spreading melanoma. Also, melanocytes are considered tumor cells once they acquire a driver gene mutation. So in our initiation phase, we have like 9 normal melanocytes and then 1 kind of jackpot cell that has that BRAF mutation. On to actually modeling the hallmarks. So for the melanocytes, which the actions of the melanocytes are in blue there, you can see that apoptosis, proliferation, and genetic instability, those are the hallmarks. The probability at which these actions happen depend on the number of driver genes in that cell associated with that hallmark. So that is D of I, which is the number of driver genes associated with hallmark I. This is something we keep track of. And the second thing that we keep track of to measure the impact of our hallmarks is the driver gene strength F. So this driver gene strength is essentially a scaling factor for what the impact of any given mutation is on the hallmark probability. Then we introduced immune cells because we needed to model immune evasion. And so these immune cells, they chemotax towards high antigenicity cells. And they also have recruitment, proliferation, and killing of melanocytes, all of which happen with a probability that is dependent on the antigenicity of the cells around them. And then those are the parameters of interest. There's a lot of parameters in our model. So I was just like, let's focus on these four. Like I said, driver gene strength F, then base mutation rate R naught. There's a base melanocyte proliferation rate B naught, and a base immune cell recruitment rate SI naught. And once we were done with our setup of the model, we needed a way to analyze it, as is the case with every model. So we looked at two different metrics. The first is entropy, which is essentially just a variance of the genome profile. And the second is average number of mutations per cell, which represents the tumor mutational burden. Both of these are calculated on a sample of our full simulation, and we use spatial systematic sampling in order to collect that. And then we have some fun observations. We actually find that there are three different intratumor heterogeneity regimes. The first is that clonal selective sweep we talked about, where a single dominant clone takes over the whole population. This is the case where entropy would be very close to zero. Then we have subclonal sweeps, where multiple subclones coexist and expand. So kind of like medium heterogeneity. And then finally, we have the fractal regime, where there's a very complex spatial structure and widespread genetic diversity. Okay. So with all of those regimes observed, we wanted to see what are the things that are impacting our simulations. But before that, some parameter estimation for growth, because it's important. So we fit our simulated tumor growth to melanoma time course data by adjusting for F, which is that scaling factor, and R naught. So here you can just see a plot of the final time it took for our simulation to reach an average detection size of 6 millimeters for melanoma or superficially spreading melanoma. And there's a very clear inverse with F, is unsurprising. But more specifically, we know that SSM takes about 5 to 15 years to become detectable, and that corresponded to a range of F being about 1.4 to 1.6. So we had a good range to start our work with. And then also look at what kind of R naught values we needed to use from the growth rates of melanoma in order to be able to match those. So we were able to get that to 10 to the minus 6 and 10 to the minus 4 also. So those are the ranges that we're working with. And on to the beloved sensitivity analysis that we've heard so much about. So this is just local sensitivity analysis, more as one at a time. And I'm only going to highlight our main sort of finding from this, which is that if you look at SI naught, that has the highest mu star value, which indicates that immune evasion is a hallmark that is actually most strongly influencing the intratumor heterogeneity that we're observing. But we wanted to look further into all of this. So we started with a quick look at the relationship between R naught, F, and intratumor heterogeneity, again, using those two metrics of entropy and of the average number of mutations or the tumor mutational burden. Okay. So I'm speeding through this a little bit, but let's see what's happening here. On the left, you have the entropy values, and on the right, you have the tumor mutational burden. In both of these, you can see that as R naught increases, so moving left to right, you do get a generally consistent increase in the entropy values. However, if you try to do the same thing for F, that doesn't work. So there isn't a clear relationship between the intratumor heterogeneity and F, but there is one between that and R naught. And then the second thing that we observe is that even when we limit our F and R naught ranges, we get a pretty decent range of entropy values that covers all three of those regimes: clonal, subclonal, and fractal. So the limitations that we put on the growth value don't end up affecting the heterogeneity that we observe. Okay. And then we wanted to look into immune infiltration and see really what is happening with SI naught that is making it so important. So in order to do that, we do a dual setup. So the BRAF mutation that we have normally does come with immune evasion, so it's a cold tumor. But we set up, in contrast, a hot tumor where that immune evasion is turned off. And we observe the density of the immune cells at 5 years into the simulation. Unsurprisingly, immune cells are more present in hot tumors than in cold tumors. But what we did find interesting was that as we increased R0, we saw higher immune cell density for cold tumors, which is unsurprising because, of course, if you have higher R0, you're getting larger tumors faster and you're getting higher antigenicity levels, higher related recruitment and proliferation levels. So it's sort of a chain effect. But what happens in hot tumors is that all of this happens at the initial phases. So the tumor doesn't get to grow big at 5 years. And this photo is at 5 years. So that was sort of our hypothesis for what was going on with hot tumors. So we wanted to look at the actual temporal changes that are happening. So here we have a plot for the normalized immune cell count at different times and different distances for tumor cells. And there's two observations to be made here. The first is that the maximum immune cell count is achieved earlier in hot tumors, which kind of supports our earlier hypothesis that recruitment is happening earlier and we're just killing off the tumors. And the other thing is, of course, that in hot tumors, you get much closer distances where that maximum is reached in comparison to cold tumors. And then moving on to the spatial analysis and how it correlates to intratumor heterogeneity. So we did a cross-pair correlation function test, which essentially tells us how different types of cells are correlating to each other. Here we categorize the cells by their number of driver gene mutations and used the highest number of driver mutations or the most aggressive cell as our reference for different R0 values. So here we have each plot corresponds to a different type of cell. So the 2 here is like the second most aggressive cell in our simulation. 2 things that we noticed. The first is that normal cells are strongly anti-clustering, which again, seems like that should be the case. And the second thing that we notice is that the second most aggressive cell type across the R0 values is strongly clustering with the most aggressive cell type. And we think that's because it's just very likely that the most aggressive cell type is just direct progeny of the second most aggressive, because all it is an addition of 1 driver gene mutation. And this is consistent across all the R0 values that we saw. And then finally, we looked at fractal dimension as a measure of how complex and space filling our simulations were for subclonal. Essentially, we just did binary masks for all the different colors in these cases and averaged out the fractal dimension. Subclonal was lower than fractal, as expected, and we managed to somehow get in the range in literature, which is, well, to be fair, very wide. It's like 1.15 to 1.75. So it wasn't a hard thing to do, but we managed to do it anyway. And that is all I have for today. This is the summary and some future work that we're hoping to get to. Thank you.
Any questions?
Very nice work, Khola. I have a question from actually, like in the very beginning, you put the list of mutations or the gene changes, let's say in melanoma, and you model those just to see how they basically, or how the tumors can behave. But there is an interesting and still probably mysterious paradigm in cancers. Like there are those driver mutations that are mutually exclusive, right? BRAF or NRAS, so they do not happen together. And maybe you would like to even expand the model to other cancer types, like in lung cancer, for example, EGFR or RAS mutations, they do not occur together. So I was just curious if your model, in a way, explained that phenomenon, because there is a sort of conflict maybe between those mutations and the tumor behavior so that they cannot occur together. Did you have such kind of explanation, or do you plan to do that?
No, so it actually we worked in reverse because we assumed that these BRAF, NRAS, and KIT were already mutually exclusive in our model. So it didn't come about as an emergent behavior. It was something that we coded in by ourselves. What is interesting though is right now we're working on different types of melanoma. So there's NRAS associated nodular melanoma, which has mobility. So it would be interesting to see if we just change the founder mutation, how that changes all of these things that we're studying.
Yeah. Oh, one more question.
It looks like from the image of the superficial spreader that the final shape ends up being very irregular, as you mentioned, because of its interactions with the local skin tissue. Do you think that it's worth considering how the local skin tissue is affecting the shape and how that might end up affecting how different clones are mixed together?
Definitely worth exploring. It's not currently in our plans, but yeah, that absolutely is an influence on what the shape ends up looking like. And as you can probably tell from some of our simulations, we don't get all of that irregularity in right now. And some of that is because our cells aren't moving. So once we started including movement, we do see more of that. So hopefully that's enough to cover our bases in this model. Yeah.
Okay. All right. Let's thank her again. Okay.